Hello and welcome to our first of what will be 3 videos on the Madden-Julian Oscillation. In this video we're going to focus on an overview of the Madden-Julian Oscillation, particularly from a qualitative perspective, as well as some of the impacts of the Madden-Julian Oscillation on both tropical and mid-latitude weather patterns. So let's dive in. So first we start off with the discussion of some of the basic characteristics of the Madden-Julian Oscillation. So first off, it's short-lived variability in the Walker circulation, roughly over the scale of 1/2 to 1 full ocean basin over the course of about a 1 to 2 week period as it passes by. It's the leading mode of intraseasonal variability in the tropics. So intra means within and season means a season. So within a season, roughly on the order of 1 month to 3 months here within the tropics. So it has a planetary scale in terms of its overall structure. Small wave number means that there's typically about 1 to 3 waves across the globe that could represent the Madden-Julian Oscillation at any given point in time. And it has a return period of 30 to 60, sometimes a bit longer, toward 90 days. So MJO events typically initiate in the equatorial Indian Ocean, somewhere between Africa and the Maritime continent. They propagate eastward at about 5 meters per second, so they're relatively slow propagating features, certainly slower than Kelvin waves. So these essential elements, their slow propagation, their eastward propagation, and their planetary scale structure are what distinguish the Madden-Julian Oscillation from other forms of variability within the tropics, including our equatorial wave modes. About half of all MJO events terminate once they reach the Maritime continent. This is known as the barrier effect, and we don't really have a good understanding as to why this effect exists. There are certainly some hypotheses that have been posed to this effect, for instance, relating to the characteristics of land versus water. However, there's no concrete understanding, no concrete basis for why this barrier effect exists. However, the other half are able to propagate onward into the Pacific Ocean, and some of them are even able to propagate around the entire globe. One thing that's important to note, we can't take the shallow water equations that we used to extract out equatorial wave modes back several weeks ago and use them to extract out the Madden-Julian Oscillation, specifically without applying any forcing to the system. When we applied the shallow water equations to the equatorial waves, we said that we could get them without any forcing, but that we often did see forcing with them in the real atmosphere. The Madden-Julian Oscillation, we can't get them without any sort of forcing. We'll show that we can get equatorial wave-like structures for the Madden-Julian Oscillation with some forcing, but there is some disagreement as to whether that's an essential characteristic of the Madden-Julian Oscillation or not. So we say that there needs to be some sort of forcing, whether that's external to the system, so from the surroundings, or internal to the system, inside of the convective envelope associated with the Madden-Julian Oscillation, in order for it to initiate. So now we want to briefly reiterate some of these basic characteristics of the Madden-Julian Oscillation. So what we have depicted here at left is a panel of 850 hectopascal zonal wind and precipitation, with the period on the x-axis and the zonal wave number on the y-axis. So we're looking at a frequency wave number diagram once again, as we did for equatorial waves. However, now the wave number is on the y-axis rather than the x-axis, and the period is now on the x-axis rather than the y-axis. This is a power spectrum, so it's measuring how much signal is present at a given wave number, and thus horizontal scale, and a given period, and thus temporal duration. And we see this area here highlighted in the blue boxes within each panel, between about 30 and 90 days, and a wave number just less than 1 up to about 3. This is all associated with the Madden-Julian Oscillation. The small wave number is what is associated with its planetary scale structure, and this long period is what is associated with the 30 to 90 day variability. Note that this period has positive values rather than negative values, and this is this diagram's way of expressing the direction of propagation. Positive values are along the positive x-axis or to the east, negative values along the negative x-axis and to the west. And so given these positive values for both fields, we indicate that the Madden-Julian Oscillation propagates slowly to the east. So its strongest signal in tropical wind and precipitation fields is at long positive periods on the intraseasonal timescales. Of note, the MJO is the only phenomenon with variability on these spatial and temporal timescales. That's not to say that there aren't features in the zonal wind and precipitation fields that also are varying on those time scales and spatial scales, but they are not coherent when they do so. The Madden-Julian oscillation is the only coherent form of variability that oscillates or varies on these specific spatial and temporal timescales. So now let's take a look at the circulation structure associated with the Madden-Julian oscillation. We have the lower tropospheric structure here depicted at 850 millibars at the bottom. We have the upper tropospheric structure here at 200 millibars at the top, between 40 south and 40 north, and 30 east and 150 west. So roughly from Eastern Africa through to the Central Pacific Ocean. This lower tropospheric circulation structure that we have depicted here has anomalously strong easterly trade winds to the east of this convective cluster, which we see indicated by the cloud as well as the upward directed vertical arrows in the middle troposphere. We also have anomalously strong westerly winds here to the west. These winds, trade winds, converge together here into its convective center, fostering tropospheric deep ascent and above normal thunderstorm activity within these regions. On the opposite side, so out here well to the east and off to the west of the diagram, we would see tropospheric deep descent. Note the downward directed arrows here, as well as below normal or suppressed thunderstorm activity on these opposite sides. These circulatory features can be viewed as the superposition of a Kelvin wave with the strong easterlies and strong westerlies at the equator, as well as an n=1 equatorial Rossby wave. Note the twin cyclones to the west and hints of twin anticyclones here to the east. However, there is some disagreement as to whether this combination of features is essential to the Madden-Julian oscillation. When we discuss Madden-Julian oscillation theories in a subsequent video, we'll indicate that several of them have this structure emerge, whereas one of them is not reliant upon this structure whatsoever. I'll note too, even though we focus primarily on the lower troposphere, the upper tropospheric fields are roughly the inverse or the mirror of what we see at the lower troposphere. Westerlies above lower tropospheric easterlies, easterlies above lower tropospheric westerlies, with the sense of the circulation features on either side of the equator being opposite what we see in the lower troposphere. The Madden-Julian oscillation results in variability to precipitation fields as it propagates eastward through the tropics. And so here we have a set of 8 panels representing different phases of the Madden-Julian oscillation, and we'll discuss these phases in a later video in a bit more detail. But here we'll just emphasize that starting up here at the top is where the Madden-Julian oscillation is originating, and then down here toward the bottom is toward the end of its propagation around the globe. The warm colors indicate wetter than normal, and the cool colors indicate drier than normal conditions on the Madden-Julian oscillation spatial and time scales. So we see an enhanced or active phase that propagates eastward, first through the Indian Ocean, then through the maritime continent, and into the Pacific Ocean, where that low-level convergence along the equator is maximized. We also have suppressed or inactive phases that precede that and trail behind that, where lower tropospheric divergence and tropospheric deep descent is maximized. So note that the Madden-Julian oscillation has its highest amplitude. These precipitation anomalies have their largest values from the Indian Ocean through to about the Central Pacific Ocean. The Madden-Julian oscillation can propagate through the Western Hemisphere, and we do see indications of that taking place with enhanced precipitation here in South America in the first couple of panels, then below normal in the next 4, and then beginning to become above normal once again in the bottom 2. But note that these anomalies are much less, much smaller, have much less amplitude than those back further to the west in the Indian and Western and Central Pacific Oceans. So its impacts can extend into the Americas and the Western Hemisphere, but they're greatest over in the Eastern Hemisphere. The MJO has distinct seasonality and variability. So what we have depicted here at left in the top 2 panels are December and March data, and in the bottom is June through September data. The top of those panels, so panels A and C, is variability in the 850 hectopascal east-west or zonal wind, and the bottom panels, B and D, are variance in the precipitation fields. And the shading in each of these panels is sea surface temperature, which we can largely ignore in this interpretation. We're really focused on the contouring that we see here. So the Madden-Julian Oscillation's latitudinal axis, the latitude at which it's centered and propagates along, moves with the seasons. It moves northward in northern hemisphere summer. So note that these white contours associated with the variability in the Madden-Julian Oscillation are primarily along and north of the equator in the bottom two panels. It moves southward in southern hemisphere summer. So those same contours in the top two panels that we see here are primarily along and south of the equator. But note, however, that the Madden-Julian Oscillation's variability, whether it's in terms of the seasonality or even its intensity, as we demonstrated on the previous slide, is greatest in the eastern hemisphere. These white contours in all four panels are largely concentrated at eastern longitudes rather than into the western hemisphere. So this is where the Madden-Julian Oscillation has its greatest amplitude, but also its greatest variability in that amplitude, and also its greatest seasonality in terms of where that feature is found, at what latitude it is found. So we can also see the maritime continent's barrier effect in these data. So the maritime continent is roughly here, here, and so on and so forth. And while we do see some variability extending just eastward from there, indicating some uncertainty as to whether the Madden-Julian Oscillation will continue to propagate eastward or not, the termination of that variability much further east from there helps to highlight the overall dampening effect associated with the Madden-Julian Oscillation as it propagates eastward. So now we want to briefly consider some of the impacts to tropical and mid-latitude weather that are associated with the Madden-Julian Oscillation. And the way that these are all manifest is very similar to what we demonstrated with our idealized video for El Nino and La Nina events. The Madden-Julian Oscillation modulates where diabatic warming in the atmosphere, and to much lesser extent the ocean, is maximized. At what longitude in the tropical region is that maximized? And so where that is maximized modulates where that atmospheric response is primarily concentrated, and then where it propagates eastward from there. So these lists are by no means comprehensive. I'll refer you to Jiang et al. 2020, which is a review of 50 years worth of Madden-Julian Oscillation research, as well as Zhang 2013, which is focused specifically on the impacts of the Madden-Julian Oscillation in the tropics and beyond, for more details on all of these and many, many more. But in general, in the tropics, the Madden-Julian Oscillation has a big impact to the monsoon, which we'll discuss next week, both when it begins, when it ends, as well as variability during the monsoon, what we refer to as active and break periods associated with monsoon precipitation. Madden-Julian Oscillation can also affect whether a tropical cyclone has a greater or lesser likelihood of forming through its modulation of ascent patterns as well as low-level cyclonic rotation patterns. It can also provide forcing to initiate the onset of an El Nino event 6 to 9 months ahead of time, particularly strong Madden-Julian Oscillation events. And you'll see more about this in the third homework assignment that covers the Madden-Julian Oscillation coming up in the next few days. It can also affect upper ocean transport both within the Indian and Pacific Oceans, as well as between the two ocean basins, all among other features in the tropics that it can affect. At higher latitudes, we see its effects in many different fields, whether that be precipitation globally, but also in the Americas and Australia and New Zealand, surface temperatures, again in the Americas, but also into the Arctic, and large-scale circulation patterns. And we often quantify these rather than looking at the large-scale 500 millibar trough ridge pattern, for instance. We use what are known as teleconnection indices to distill down that large pattern across a wide range of longitudes into a single metric or single number that quantifies its basic shape. So looking at a couple of these in a little bit more detail, we can focus first on tropical cyclone activity. And here we have 4 different panels representing combinations of Madden-Julian Oscillation phases, generally propagating from the Indian Ocean with its active phase eastward through into the Pacific Ocean and ultimately to the Western Hemisphere. The green shading in each of these panels indicates above normal precipitation, the brown shading indicates below normal precipitation, and the black lines are tropical cyclone tracks. We have similar numbers of days within each of these categories, so we shouldn't expect to see massive differences in tracks apart from the Madden-Julian Oscillation. So in terms of precipitation, as we saw on a previous slide, we see the propagation eastward of anomalously high precipitation associated with the Madden-Julian Oscillation through time, through its phases. But we also see anomalously high tropical cyclone activity following along with that. Note the dense packing of tracks here in the southern Indian Ocean near to this area of enhanced precipitation. We see that in the western North Pacific here in this panel, and especially this panel. And then we see that pick up here in the eastern North Pacific in the final panel as well. So as the MJO's convective envelope associated with its active phase propagates eastward, so too does an area of enhanced tropical cyclone formation potential, at least during the portions of the year when tropical cyclone formation is otherwise favorable. We could have a Madden-Julian Oscillation event propagate through the Western Hemisphere in February, but the background conditions aren't favorable for tropical cyclones to form then in either the Eastern Pacific or the Atlantic. It's only when it's otherwise favorable on the large scale where the Madden-Julian Oscillation can help provide that extra impetus or boost to the formation potential. In terms of large-scale circulations, we have two different phases of the Madden-Julian Oscillation. Phase 2 here at the top is where the active phase is located in the Eastern Indian Ocean, and phase 6 here is when it's located in the West Central Pacific Ocean, as indicated by the gray clouds within each of these panels. I've also highlighted in black the general sense of the large-scale 500 hectopascal pattern associated with what the color shading is indicating in each of these panels. And so in phase 2, and whether it's with a lag of 1 day, 2 days, or 3 days from that Madden-Julian Oscillation event forcing, we see enhanced ridging in the Pacific Ocean with enhanced troughing along the west coast of North America. Whereas with phase 6, we see enhanced troughing in the Pacific Ocean with weak ridging across central and eastern North America. And these all again are manifest through changes in where diabatic warming associated with tropical convection, here enhanced or suppressed by the Madden-Julian Oscillation, are located. These help to trigger what are known as Rossby waves along the subtropical and then ultimately the mid-latitude jet that then propagate along those jets and perturb the downstream weather patterns as they do so, generally decaying in amplitude as they propagate further to the east. However, they can affect the downstream weather patterns in a way that then reinforces the impact indirectly through a weather event downstream and allows that impact to propagate even further to the east or downstream in association with a Madden-Julian Oscillation event. Finally, and perhaps most notably for us here in the United States, is the Madden-Julian Oscillation's impacts on United States winter temperatures. While it can have an impact on temperatures throughout the year, its impact is most notable in wintertime when the large-scale weather patterns that affect our weather are best defined, have highest amplitude and longest wavelengths. So we see here composites for December, January, and February for different phases of the Madden-Julian Oscillation. So again, phase 1 being when it's active in the Western Indian Ocean, and then propagating eastward through phases 4, then 5 through 8. So we go down on the left side, come back to the top on the right side, and go down from there. Warm colors indicate above normal temperatures, blue colors indicate below normal temperatures. This particular diagram doesn't indicate statistical significance of these. There's separate data available from the Climate Prediction Center's website that has that information. In general, only the brightest red and darkest blue are actually statistically significant because of the large degree of variation within the system. But taking this as a specific example, in December through February, when the MJO's active or westerly phase is somewhere between roughly the west coast of Africa through the Indian Ocean, we see below normal temperatures in the central and eastern United States. However, when that active phase is somewhere between the maritime continent and the west central Pacific Ocean, we see above normal temperatures on average with those MJO phases, all through their modulation to the large-scale weather patterns that facilitates either a trough with phases 8, 1, and 2, or a ridge with phases 3 through 7 into our vicinity here. But again, there's a lot of variability within this data, and in homework 3, you'll explore cases where this is a good match and where this is a really poor match to what actually happened in terms of large positive or negative temperature anomalies here in the upper Midwest. So that wraps up our discussion about the Madden-Julian Oscillation and its basic impacts and characteristics. In our next video, we'll discuss 4 theories that have been posed for why the Madden-Julian Oscillation exists and why it propagates slowly to the east on the planetary scale. But for now, that's all on this first video.